Hello, my name is Nick Mowry, and in this video, I'll be covering the message queuing telemetry transport for sensor networks. To provide some context for the way this network protocol behaves, I will briefly cover its origins and, to a greater extent, the architecture of standard MQTT, since many of its features have been carried over into MQTT-SN. MQTT has its roots in IBM's MQ WebSphere. This was one of many protocols that had its specific usefulness, but as new use cases emerged, the protocol was modified to fill these needs. In this case, the specific need was a lightweight and bandwidth-efficient protocol that was data agnostic with support for variable network reliability. In the early 90s, ConocoPhillips, like many other industrial customers, used PLCs in their refineries to connect various sensors in their equipment. Once it became available, these systems were connected across millions of square feet using supervisory control and data acquisition to analyze data and control machine actuators. Of course, these data being sent required a robust network due to the critical nature of the equipment being controlled. The system worked well for wired systems with unlimited bandwidth and energy supply. They could provide data at 1200 baud and grab all the data required to keep the refineries humming. However, this approach was not well suited for monitoring the entire length of their oil pipelines. With over 10,000 miles of these pipelines, SCADA was not ideal. Sensors along these conduits communicated via satellite connection, which were metered. That is to say, payment per unit of data sent and received. Quite expensive. Most data being sent and received was not entirely critical. If data from flow sensors in the pipeline is absent for a minute or two, it was not a big deal. However, a missed command to engage a valve intended to staunch the flow of a ruptured section of pipeline must be delivered quickly and with certainty. SCADA treats these two levels of data messages, with equal importance to ensure that critical messages are all delivered. Seeing the cost incurred by an invariably robust system, engineers from IBM and Eurotech developed the MQTT protocol to reduce the impact of this waste. To do this, they understood that there were 5 key aspects by which any successful solution must satisfy. First, it needed to be simple to implement. To the right, you can see a bare bones Arduino sketch, which functions as an MQTT client. Including white space and formatting, it numbers about 60 lines of code. In the loop function shown here, you can see it calling the MQTT client loop, which handles the wait time between sending and receiving messages. Today, installing this on an Arduino is a fairly straightforward process with readily available source code and inexpensive hardware. At the time of its development, implementing MQTT would certainly have been more difficult, but given the simplicity of the code, still well within reason. It also needed to be lightweight. To provide some context, the compiled sketch shown here accounts for around 20% of the memory available on a $3 Arduino. Again, this represents current day hardware, not that available during the time when this protocol was developed, but it still gives plenty of room for any type of additional logic required to interface with sensors and perform in-network processing. Furthermore, it needed to be ambivalent to the types of data it was transporting. In this way, it could handle intermittent sensor data as well as controls for critical hardware. The protocol also needed to be able to handle data intended for clients whose connectivity could be compromised. Finally, it needed to have the ability to allow nodes to specify the importance of every message, both on transmission and receipt. MQTT fundamentally is a publish-subscribe protocol. The illustration here shows a single direction for messages, but it is bidirectional. This allows clients to connect as a publisher, subscriber, or both. All clients connect to a broker, which handles all the messages passed through the network. The MQTT protocol runs on top of the TCP/IP network stack. Some of you reading this first line thinking this whole thing is an overlay. What's the point? Extra layers means extra overhead and reduced network life, etc., etc. Don't tune out just yet. MQTT is an overlay. In order to meet the 5 goals described previously, MQTT was designed to work on the network available in its day to achieve a level of simplicity and interoperability. The MQTT-SN protocol, like many other sensor network architectures, has evolved over the years and has its roots in MQTT. If it helps to do so, think of MQTT as a parent class and MQTT-SN as an inheritance class. This analogy, although just an analogy, is suitable to at least the extent that all the message handling protocols in MQTT-SN are those found in MQTT, with the addition of more whose efficiency is better suited for sensor networks. We'll cover those later, but for now we'll discuss the commonalities. We'll start by dissecting the message. Every message has a header with a minimum length of 2 octets. Depending on its use, the message may be comprised solely of this header with the payload contained therein. The size of the payload header may be 1 to 3 octets in length. If a larger message is required, this can be specified and the message can be up to 256 megabytes. Now down to terminology. A client is any node in the network. In the MQTT architecture, a client can both publish or subscribe to messages sent across the network. A broker acts as a message server within the network. When a client wishes to send a message on the network, it must first connect to the broker. Brokers are distinct from clients, and one cannot perform the duties of the other. Once a connection has been made between a client and the client can publish or subscribe to a topic. For the standard MQTT protocol, topics have a hierarchical structure allowing for clients to publish or subscribe to all subtopics within a higher level of the structure. For example, if a client running on a mobile device wants to gather all data from one room in a smart home, it can subscribe to this level of the hierarchy and then parse out the data as it comes. Similarly, a database client can subscribe to all network traffic, allowing it to create a digital twin for all home activity. As mentioned earlier, all connections are layered atop a TCP/IP infrastructure. This infrastructure handles all the naming and connectivity between the clients and the broker. The quality of service, I think, is one of the most crucial aspects of the MQTT architecture. When they set out to create this protocol, Stanford Clark and Nipper realized that not all messages are created equal. To reduce waste for a less critical message, they devised a method for assigning an importance to a message. For reference, these quality levels are listed in ascending order of energy and bandwidth consumption. Let's consider the use cases for these different levels. For at most once quality of service, let's consider a sensor node collecting audio data. For the sake of bandwidth, it probably wouldn't be sending raw digitized sound, but more likely it would be sending a message with an amplitude, frequency, or duration of an extended audio event or series of discrete audio events. For this example, we will assume that this sensor node is publishing messages about semi-regular signals it detects. For this type of signal, we can use at most once delivery method. Messages sent by this method are sent only once. If they arrive, great. If not, that's okay too. There will be more messages following this one, and the overall significance is not greatly affected by a certain percentage lost in the shuffle. This level places the least demand on the network, but the subscribers who use messages in this topic must be able to handle multiple messages. Now, what happens if one of these messages is dropped? Do we care? Probably not, and neither does the sensor node. It never hears back regarding the success or failure of messages sent at this quality of service. It's fairly safe to assume that what actually happened is lost in the network, and the brief interruption should be disregarded or smoothed out with averaging or some similar scheme. The use of at least once delivery gives the node the ability to ensure a message has been delivered successfully at least once. Let's continue our audio sensor node example. In addition to distilling the gist of the message, i.e. amplitude, some small logic could also be used to set a threshold for this amplitude value. In such a case, perhaps the network is trying to acknowledge the presence of ambient sounds like crickets or a light breeze, but wants to notify the network immediately if it detects a louder noise like a tree falling in the forest. Or, to follow our previous example, it might disregard the constant hum of a refrigerator, but would send notice if it heard a loud noise like a breaking window. Just as the name implies, the use of at least once delivery gives the node the ability to ensure a message has been delivered successfully at least once. Let's continue our example audio sensor node. In addition to distilling the gist of the message, stand by. I'm not going to record this more than once. I apologize. For exactly once, so we've covered quality of service at most once, which allows for disregarding some drops in the network. We've covered at least once, which makes sure to deliver critical messages when it finds them. And we also have exactly once. When a receiver sees that it has received a message intended to be delivered exactly once, it processes the published message accordingly and replies to the sender with a publication received packet that acknowledges the published packet. If the sender does not get a publication received packet from the receiver, it sends the published packet again with a duplicate flag until it receives an acknowledgement. Once the sender receives a publication received packet from the receiver, the sender can safely discard the initial published packet. Sender stores the publication received packet from the receiver and responds with a publication release packet. After the receiver gets the publication release packet, it can discard all stored states and answer with a publication complete packet. The same is true when the sender receives a publication complete. Until the receiver completes processing and sends the publication complete packet back to the sender, the receiver stores a reference to the packet identifier of the original published packet. The step is important to avoid processing the message a second time. After the sender receives the publication complete packet, the packet identifier of the published message becomes available for reuse. This is the slowest quality of service level since there are 2 flows required for the message to be delivered. And that was all a mouthful, but you can see here laid out, it is indeed very duplicitous in the amount of messages that are sent back and forth. That is to ensure that the receiver gets exactly one message, as the name implies. So with quality of service, we can assure that a message will be delivered if necessary, but what happens when the recipient is not available? MQTT has a protocol for this as well. Message persistence allows the broker to cache messages, and the subscriber can collect them when it reconnects. This may be due to network failure or planned sleep by the node to conserve energy. In this illustration, we see a client connecting to a broker in a non-persistent session. Here you can see that the client only gets messages after it subscribes to a topic and until it subscribes or disconnects. In this illustration, we should assume that the client has subscribed to a topic during a previous persistent session. Once reconnected, the broker supplies the client with any missed publications during its absence. Messages are only cached in this way if quality of service levels 1 or 2 are specified. Here's where we can start to differentiate between MQTT and MQTT-SN. If the sensor network in the sensor easy for me to say, excuse me. In the sensor network version, there are 3 components: clients, forwarders, and gateways. Gateways are similar to brokers in the standard MQTT topology in that they are the hub of the wireless sensor network. However, the functionality is not replaced, simply augmented. In this way, it is possible to connect an MQTT-SN network with a standard MQTT network without a lot of extra work reformatting messages and reinventing packet types. Here's another illustration showing how the MQTT-SN and MQTT networks can be used in conjunction with a wide variety of devices with differing energy and data demands. In this particular case, a smart home is illustrated with a smart thermostat and a smart door lock. These are MQTT-SN clients interfacing with an MQTT-SN gateway. Within the gateway, it also acts as an MQTT client, which then can connect to an MQTT broker, which can then supply these signals to any other MQTT client connected to the broker. Gateways in the MQTT-SN protocol can be transparent or aggregating. In a transparent gateway, the messages are one-to-one from the clients through the gateway to the broker. In an aggregating gateway, the messages are many-to-one. The MQTT-SN protocol adds another level to the quality of service. This level, designated QoS -1 or binary 1-1, and it uses a predefined topic and gateway name and does not attempt to connect. It does not listen for a reply. The gateway, upon receipt, simply forwards on the message to any interested nodes without queuing them. MQTT-SN has certain strengths: the quality of service. These variable levels of message delivery assurance allow for energy efficiency so that each message is handled according to how important it is and what it means to the network. It's a mixed it can be used as a mixed architecture in that it can interface with wired MQTT networks that are already existing. It's designed specifically for efficiency to run on low-powered wireless networks and battery-operated devices, and it explicitly supports sleeping clients. It's approachable in that it's easy to implement, and it's designed specifically to work on top of wireless networks like the Zigbee or Bluetooth Low Energy. And it, to some degree, a small degree I would say, it supports dynamic discoveries of gateways which allow it to be somewhat self-organizing. Now, where it sort of falls down is the scalability. Gateways and broker are limited by bandwidth, so you can only have a certain number of clients connecting to any gateway or broker. If you're trying to canvas a large area with many nodes, you would have to have an increasing number of gateways or in order to cover all of these nodes. And that's because the architecture is more or less static. You can add elements to the network, but you have to know what the element is going to do, namely its function as a client or a forwarder, and it can only perform that function in the network. It does not account for order delivery, although if that were necessary, I think one could fairly easily add a timer to a piece of hardware and send that along with each message if required. There's no security, which is not I guess not that uncommon for wireless sensor networks. And there's a somewhat narrow interest. You cannot subscribe to multiple topics with one subscribe message. This is depending on how you set up your hierarchy within the network. This is more or less true. Some opportunities for MQTT-SN where it might shine within network processing. With a small memory footprint, this protocol is capable of doing more onboard processing and sending messages only when necessary. This could be leveraged in sensor networks where urgent messages are the rare exception. I think also small semi-static networks are more ideally suited for this protocol. If all sensor nodes can be located within the range of one gateway, then an MQTT sensor network could be used to gather large quantities of data rapidly. Terrain data, for example, could be collected rapidly with a handheld gateway and several autonomous drones acting as clients. And I think physically large networks expanding beyond the broadcast range of a gateway uh, with intermittently connected nodes. I think a possible use case for this could be the previous example with the autonomous drones, only scaled up, allowing for these drones to survey much larger areas not covered by the gateway broadcast range. They could go about collecting data to the extent that their batteries would allow, and upon return, dump their data during a recharge cycle. Thank you for your time.